This video is brought to you by Wondrium. Click the link in the description to sign up for free and support this channel. Planets being born in cosmic dust. A comet colliding with Jupiter. Galaxies in the midst of crashing together. Thousands of galaxies in a tiny portion of the sky we thought was empty. A new form of cosmic energy that appears to be accelerating the expansion of the universe. This is just a small sample of the thousands of astounding discoveries made by a school bus-sized telescope we launched over 30 years ago, called the Hubble Space Telescope. Hubble was like the Earth getting a pair of glasses to correct its myopic vision of the cosmos. We could suddenly see things we didn't realize we couldn't even see. Every new photo was even more beautiful and remarkable than the one before, and we still marvel at the discoveries that Hubble helped make. But 31 years later, in 2021, we humble humans have launched an even bigger telescope that is at least 100 times more powerful than Hubble, called the James Webb Space Telescope, or JWST, and it's about to blow our minds. We're already beginning to see celestial objects with unprecedented resolution. We will probably discover things we had no idea we should have even been looking for. What makes the JWST so powerful? How does it actually work? And what might we see through these new pair of glasses? That's coming up right now. At its core, a space telescope is a digital camera. It takes pictures, just like the camera on your phone. The difference is that a space telescope is more powerful and is specialized to take pictures of things very far away. To appreciate the design and capabilities of the James Webb Space Telescope, let's quickly look at how an ordinary digital camera works, and then I'll point out the components replicated on the JWST. To take any digital picture, you need three things: light, optics, and a sensor or recording device. The central part of the camera is a sensor which records the light. A sensor in a camera is often made of millions of small pixels. What's a pixel? Well, a pixel is the smallest element of the sensor that can interact with light to produce a current. When a photon hits a pixel, an electron in the pixel absorbs the energy and becomes dislodged from its orbit, allowing it to move freely. By using a material like a semiconductor, we can use these free electrons to create a current, resulting in a voltage. The amount of light absorbed by the pixel determines its brightness intensity. Areas of the sensor that receive less light will be dark, and areas that receive more light will be brighter. Generally speaking, the more pixels there are in a given area of a sensor, the higher the resolution and the more detail we can record. We have to be careful not to overexpose or underexpose a photo. Overexposure is when too many photons are sent to the sensor, sometimes resulting in a completely white photo, whereas underexposure results in a dark photo because of a lack of photons. It's thus important that our sensor gets the correct amount of light for the setting. On a camera, there are a few ways this is achieved. One way is to control the amount of light coming to the sensor by changing the aperture. In other words, we can increase or decrease the hole through which the light flows on through to the sensor. If we decrease the size of the hole, we decrease the number of photons. And likewise, increasing the hole size results in increasing the photons. We can also change the exposure, which is the time duration over which we collect photons. If we collect for a long time, we get more photons and thus a brighter picture. Likewise, if we collect light for a shorter time, we get fewer photons and a darker picture. This leads us to the last part, optics. These optics guide the photons to the sensor. In ordinary cameras, this is done by a lens, which bends the light and refracts it to a single sharp point. Now that you know how a camera works, let me point out the major differences in how a space telescope works. First, overexposure is not a problem because telescopes like the Hubble and JWST are made to look at things very far away. It means that inherently very few photons will be reaching the sensor. The field of view is quite narrow and things are just extremely dim. Underexposure is the main issue telescopes face. There are very few photons to be had from objects very far away. This is because the number of photons are spread over a greater area the farther away you are from the source. And with telescopes like the Hubble and JWST, we're dealing with some of the farthest objects in the universe. So we have to try to capture every precious photon. Instead of using a lens for optics to bend and refract the light to a sharp focus, the JWST uses mirrors to do this. There are two ways we can maximize the number of photons received. One is to make the surface area of the mirror as large as possible, so as to capture the maximum amount of light. This is equivalent to increasing aperture on a camera. This is the reason scientists created the largest practical folding mirror system that could fit inside a rocket. Second is to increase exposure time so that we can trap more photons over time. This means that the telescope apparatus has to be very stable so that it can focus on the same object for a prolonged period of time without any change in the precise direction where the light is coming from, so as to not blur the image. To see what I mean, try to take a photo on your phone with an exposure time of just 1 second. Unless you use a tripod, you can bet the photo is going to be pretty blurry. Let's now look at some of the technology that makes the JWST so much better than anything we've had before. First, the mirrors on the JWST are a whopping 6.5 meters across. This is a huge improvement over the Hubble telescope, which had a primary mirror only 2.4 meters across. Simply speaking, this means that the JWST can capture more than 6.5 times more light than Hubble can. And as we discussed, more light means you can see more faint objects. It has also been designed to see infrared light, which is why its primary mirror is gold, because gold reflects infrared light better. Why is it designed for infrared light and not primarily visible light like the Hubble telescope? Infrared has many advantages. In infrared, you can see through space dust better. This is because visible light is absorbed or scattered by the smoke-like dust and debris, because visible wavelengths are the same order of magnitude as the particle dimensions. Infrared radiation, on the other hand, has wavelengths an order or two of magnitude larger, and so is not so readily scattered and absorbed. This is critical for observing things far away because there's a lot of dust between us and distant objects. In addition, infrared will allow the JWST to see things farther away and further back in time because the most distant objects can only be seen in infrared. This is due to optical light from these objects undergoing redshift because of the expansion of the universe. And the JWST doesn't have just one sensor to detect this light, but uses 4 different scientific instruments, including 4 cameras, to capture different wavelengths of light and other information. It can even perform spectroscopy, or measure the exact wavelength of the incoming photons. This will give us some clues about the origin or source of the light. Here's how it all works together. Infrared light travels from distant objects through space, through dust and debris, and this telescope's primary mirror. It is then reflected onto the smaller secondary mirror into what's called the aft optic system, which further focuses and refracts the light before it goes into the sensors, also called cameras by NASA, located behind the mirrors. Another major difference between the JWST and Hubble is that while Hubble orbits the Earth at only about 547 kilometers above its surface, the JWST orbits the Sun at about 1.5 million kilometers away from Earth. Hubble orbiting so close to the Earth leads to some problems. First, since its orbital period is only 95 minutes, it goes in and out of Earth's shadow during this short period of time. When it's on the Sun's side, the intense light from the Sun can lead to distortion and overexposure. When it's in the Earth's shade, the reflected light from the Moon can interfere with the camera, and the Earth could block what it's targeting to see. These issues significantly reduce the usefulness of the telescope. To fix this and be able to constantly capture light from the universe, the JWST has a few tricks up its sleeve. Instead of orbiting the Earth, it orbits the Sun at something called the L2, or second Lagrange point. What are Lagrange points? Well, there are 5 of them. It's kind of a happy accident of gravity and orbital mechanics. They are special points in space where gravity from the Sun and Earth perfectly balances the orbital motion of a satellite so that it stays put in a stable orbit. What this means is that a satellite in any of these 5 points will stay in a fixed position relative to Earth and the Sun, with minimal course correction required. The balance of forces acting on the satellite keep it in place almost on its own. It so happens that the L2 Lagrange point is 1.5 million kilometers from Earth, which is about 4 times farther than the Moon. Here, it will constantly follow the Earth's orbit around the sun. You'll notice that the telescope is not still, but in a small orbit around a point perpendicular to its orbit around the sun. This is to ensure that the telescope is not constantly in Earth's shadow, because then its solar panels would not work. Furthermore, in order to take the most sensitive pictures ever taken, it's essential that the telescope doesn't receive any photons from the sun, which would overexpose and ruin the image. The simple but clever trick scientists used to solve this problem is a sun shield, not unlike a sunshade you might use in your car. The telescope is oriented such that the side facing the sun has a huge shield the size of a tennis court to block out the sun's light. It's made of 5 very thin layers of highly reflective plastic-coated foil. They're so effective that on the hot side, the temperature is up to 110 degrees Celsius. But on the cold side, where the primary instruments of the telescope are located, the temperature is as low as negative 237 degrees Celsius, or only about 36 degrees above absolute zero. This allows the instruments to stay undisturbed by photons from the sun, allowing it to focus on the photons from outer space. So what do we expect the JWST will see when it looks out into this final frontier? The oldest light in the universe and the oldest objects in the universe are very dim and in the infrared range. Because the JWST can collect more photons from its larger surface area and is designed for infrared light, we can expect to see objects and light from some of the earliest history of the universe, including the formation of the first stars and galaxies. Who knows what we might discover? And the images should be even sharper and higher resolution than Hubble, not only because of the bigger size of the mirror, but also because the JWST uses more modern and advanced instruments. For example, the camera design uses some advanced components including mercury cadmium telluride. It's a crystal that was grown in a lab. The unique thing about these crystals is that it can convert infrared light into electricity, allowing the infrared light gathered by the telescope to be turned directly into digital signals that can be read. These cameras are so specialized they had to be built by hand. Since there's also a spectrometer on the telescope, we can also do spectroscopy. The concept is that different atoms and molecules absorb different wavelengths of light. By looking at what type of light gets absorbed on a planet, we can get a good idea of what type of atoms and molecules are present on the planet. In other words, we'll be able to detect the composition of the atmosphere on alien planets. So, for example, we'll be able to look for things like water, oxygen, methane, and ammonia, which can be biosignature gases. We'll even be able to detect the type of weather on exoplanets. There's a chance we might see something that looks like life. Yes, the JWST could detect possible alien life, or at least a strong indication about whether life might exist on an alien planet. The overall goal of the JWST is to understand our universe better and uncover its mysteries. Even preliminary pictures it took to check the sensors and equipment on board already look extremely good. And I agree with NASA scientists that say that the James Webb Telescope is about to change astronomy. And I think it's going to blow our minds. So get ready for the ride. And if you want to prepare for the astronomical discoveries that are almost certain to come, I highly recommend arming yourself by learning the fundamentals of astronomy. There's a great course available on Wondrium, today's sponsor, that will help you do this. It's called Understanding the Universe, an Introduction to Astronomy. It's a detailed 96-lecture college-level course taught by one of America's foremost astronomers, Alex Filippenko, whom you may have seen in many documentaries on TV. He starts by taking you on a tour of the cosmos, goes through almost every aspect of astronomy, including the workings of telescopes, properties of light and waves, various types of celestial objects, including black holes and wormholes, to dark matter, dark energy, and the Big Bang. It's a fascinating, comprehensive course taught in a simple-to-understand manner by a great teacher. You'll find this and many other wonderful courses on Wondrium, taught by some of the best educators in the world. I've been a member of Wondrium for a long time. I enjoy it so much that you'll even see my testimonial at the bottom of their homepage. It's really easy to sign up because they're offering a free trial and you can cancel at any time. So you have nothing to lose, only a lot to gain. If you like to have more than just a cursory knowledge of subjects like astronomy, then be sure to click the special link in the description to take advantage of this free offer. That link is wondrium.com/Arvind. That's wondrium.com/Arvind. And you'll be supporting this channel when you sign up. So I want to thank you for that. And if you enjoyed this content, then be sure to hit the subscribe button so that you can be informed the minute I post a new video. And if you have any questions, please leave them in the comment section. I try to answer most of them. I'll see you in the next video, my friend.